Okay, yeah, so let's, well, bear with me. Let's take a look for homework 8 and exercise 1. So we have y1 to yn IID, and then PDF having this formulation for each one of the random variables. And then we want to show that this theta hat, which is sum of yi squared over n, is the unbiased estimator of the theta, where theta is the parameter of this PDF. Okay, and then is theta an efficient estimator? Yeah. Okay, so maybe let's write down some. Okay, f of y. Well, personally, I like to use semicolon. I don't because for the parameter. Okay, but based on your preference, you can use vertical bars for that. But usually, use a vertical bar is referring that the theta is also a random variable, and then you're talking about statistic in the Bayesian frameworks. But for me, I like to use semicolon, just to distinguish the conceptually. Yeah. Okay, so 2y over theta, and then exponential of negative y squared over theta. Okay, so we want to estimate theta, and then let's see. And then what we define is that our estimate is summation of yi squared over n. So our goal is to check whether expectation of theta hat is equal to theta or not. That's one thing we want to check. Okay, let's see. Okay. Yeah, so we're going to approach this in the following way. So we're going to let x equal to y squared. And then we are going to find the distribution of y squared. So we're going to use the change of variable using the CDF method. So let's start from the CDF for random variable x, which is the one that we define here. And then this is just the probability that a random variable x following a particular observation. And then substitute with the variable that we are that we know of, which is the y less than the x. Okay, and this is also equivalent to random variable y less than square root of x. And what is also implying here is that this y must be greater than 0. Okay, but just a detail. And this is just the CDF for the random variable y, but evaluated at the square root of x. Okay. So now we interested is the PDF for the random variable x, which is from our definition here for x. And this can be found by taking the derivative with respect to x for the CDF under the random variable y evaluated at square root of x. Okay. So here we just need to take the chain rule. So one is the derivative with respect to the square root of x, and then also the derivative of the CDF for your random variable y, which turns out is just the PDF of random variable y. So you just need to plug in the the lowercase, the PDF of y, and then also evaluate it as square root of x. So the PDF of y, which is given here, which is what we know of, or that the information that we have that we start with. Okay. And next we just plug in the individual pieces to complete this PDF for x. Okay, so the derivative of this would just be 1/2 x raised to the power of 1 over 2. And then the PDF is just this one. So we have 2. But everything here should be evaluated as square root of x. So we have, let's say, maybe we can write it as 2 multiplied by x by raised to the power of 1/2, and then over theta. And then exponential of negative x over theta. Okay, and then you can further simplify that, and then you will end up with this form here. So what is the distribution for the PDF that having this form here? I'm asking a question. So what is the distribution of this one? Or what do you call this distribution?
Exponential.
With parameter
1/θ.
1 over theta. Okay. What is the expectation of x here?
Theta.
Yeah, so basically it's 1 over theta, right? So it's just theta, yeah. Okay, so once we have the distribution for x, now we can go back to our original question, expectation of theta hat. So E of theta hat, which is the expectation of summation of yi squared over n. This is also equivalent to summation for the expectation of yi squared over n. And then the expectation of yi squared is just the expectation for a random variable x. So that is just theta over n. And then here we have so we have the sum over n copies, so which is n copies of theta, and that will give us theta. So that it will give us, so the expectation of theta hat is theta. Okay, so I think that should answer the question that this is an unbiased estimator. But is it an efficient estimator? Okay. Any comments on how to show whether this is an efficient estimator for theta or not?
We need to find the lower bound.
Of, or lower bound of what?
Is the
Mm-hmm. And then we want to check the variance, whether equal to that or not. And then if it is equal, then we can say that it's efficient. Okay, yeah. So I'll just comment. So yeah, I'll just comment without writing some of the details. But that will be your procedure on how to check whether it's efficient or not. Yeah. Okay. Yeah. Then any question or comments for up to this point? Okay, then let's take a look at part B. So yeah, x1 to xn IID, and then each of them follow a general normal, mean, mu, and sigma. And then both of them are unknown, and let S squared be the sample variance, be the unbiased estimator of sigma squared, and show that the efficiency of S squared is less than 1. Okay, so yeah, let's make a few comments on this one. So this is for part B. So S squared is the sample variance, so which is referring to this formulation, xi minus x bar square and then over n, n minus 1. So it's referring to the sample variance. Okay, so that will be the setup for x squared. And then what we are interested is that the efficiency. So in the end, we want to calculate this ratio. So 1 over the Fisher information for sigma squared, because the question was saying this is the unbiased estimator for sigma squared. So the efficiency that we want to evaluate is that the 1 over Fisher information, which is also the what do you call that? The Kramer-Rao lower bound, and then over the variance of the S squared. So we want to check this one, whether it's greater or less than or equal to 1. So that will be our goal here. Yeah. So first of all is that we are talking about the sample variance. So this is the formulation for the sample variance with divided by n minus 1. And then we also know that this is the unbiased estimator for sigma square. Show that the efficiency for S squared is less than 1. Okay. So we already know that we want to show that this is less than 1. Okay. Okay, so this is what we are going to do for this one. Okay, once we set up the question, now we just need to calculate the numerator and the denominator for these two terms. Yeah, so maybe let's calculate on the Fisher information, which is the numerator here. Okay. So yeah, let's start with the PDF, which is basically just a normal. So x is just a general normal with mean, mu, and sigma. So this is the standard deviation. Okay, so 1 over 2 pi sigma squared. Okay, multiplied by the exponential of negative 1/2 sigma squared, then x minus mu squared. Okay, so this is just the PDF. Okay, so now let's write down the log likelihood, which is essentially the log of the PDF. And let's denote it as L of, let's say, let me ask a question here. So what is the difference between the log likelihood and the PDF function? Conceptually, what is the difference between this L of mean, mu, and the sigma square, and this f of x? What is the difference? Because as you can see, just taking the log of the PDF and then it does not change anything. But what is the difference conceptually?
Turns multiplication to sums.
That is operational wise, but or what is the statistical meaning between the differences between log likelihood and the PDF? So the PDF is the probability density function, and the log, the L is the log likelihood function. Okay, so the difference is that this PDF here, it's a function of your random variable. So you can change your observation or random variable, and then you will get the corresponding density for the particular observation. So it's a function of your random variable. And here, the log likelihood, it's a function of your parameter. So the parameters that you define this probability distribution. So that's the conceptual difference. So when you work on estimation problems, so usually you will work with log likelihood function. So log likelihood function again is a function of the parameters. So then when you're taking derivatives, say first order derivative and then second order derivative to find the maximum or minimum. So if you want to minimize the negative log likelihood, so then you are taking the derivative with respect to the parameter, because the log likelihood itself is a function of parameter, so not the random variable anymore. So that would be the conceptual difference. Does that make sense? Yeah, so the likelihood function is a function of parameter, while the PDF is a function of your random variable. So we're basically looking at the same formulation. They look exactly the same, but from a different perspective. One is from the perspective of a random variable, and the other one is we look at the same formulation from the perspective of a random of the parameter. Okay. Okay. So now we're just taking the log transformation, but conceptually it's totally different. Okay. So just taking the log of that, we will have negative 1/2, and then log of 2 pi and then the sigma square, minus 1 over 2 sigma square and then x minus mu square. Okay, so now we express this formulation as a function of mu and sigma square. And then to find the Fisher information matrix, now we're going to take the derivative with respect to the parameter. And then for the log, maybe we can just use the lowercase l of mu and sigma square. So now it makes sense to take the derivative with respect to the parameter for a function that is a function of involving parameters. Yeah. That would be the conceptual difference. Okay. So now we just need to solve for this derivative. Let's see. Yeah, so we have negative of 1 over 2 sigma square, and then plus 1 over 2 sigma raised to the power of 4, and then x minus mu square. Okay, and then to evaluate the Fisher information matrix, or for this particular parameter, we also need to take the second order derivative. So it's just based on your preference of the notation. Yeah. How do you want to express as the second order derivative? And this should give you a 1 over 2 multiplied by sigma raised to the power of 4 minus 1 over sigma raised to the power of 6, and then x minus mu square. Okay, so that is just the second order derivative. And we also need to evaluate the expectation for that. And that is just the definition for the Fisher information matrix. Well, we're only talking about the sigma square for now. Yeah. Any question or comments for up to this point? Because for the rest, it's just the plug in the formulas for and then calculating. And then we need to evaluate this expectation for this second order derivative. That would just be the Fisher information matrix. So that is just the definition part. Yeah. And then we plug in the corresponding components. Okay. Yeah, so any question up to this point? The rest is just the simplified arithmetic part. So any question up on the procedure or the conceptual part? Okay, yeah, so now we just need to just perform simplifications. So the expectation here is only going to apply on random variable. So the only terms that involving random variable is the x here. So we have negative of the constant, so 2 sigma raised to the power of 4, and then plus. So you can expanding the square and then plug in the expectation. So now I'm just going to directly write down the answer. So after you expanding the terms and then plug in the expectation, you will have sigma squared over sigma raised to the power of 6. So that will reduce to sigma raised to the power of 4, and then you will end up with 1 over 2 sigma raised to the power of 4. Okay. Any question? Okay, so maybe just to summarize, first of all, we start with the sample variance. which is the formulation of this one. And then we are interested in the efficiency to check whether it's greater or less than 1. And then this efficiency is defined as the Cramer lower bound over the variance for your estimator S squared. So here, up to this point, we are only working on the numerator. And then to express the numerator, we first find the log likelihood function, which is taking a log of the probability density function. And then once we have the log likelihood function, which is a function of the parameter, and then we further taking a derivative with respect to the parameter of interest. So in this question, we are only interested in the sigma square, but you can also take a derivative with respect to the mu, and then to find the, say, the same thing for the Fisher information for the sigma term, for the mu, and also for the efficiency for the mu. But that's another story, which is not asking here. So after we have the log likelihood function taking a derivative with respect to the parameter of interest, and the second order, we'll have this expression. To complete the Fisher information matrix, we need to evaluate the expectation. So we plug in these terms here, and then evaluate the negative expectation, resulting in this one. So that will be that's what we have been doing so far. Okay. So next, we need to further complete this ratio here. Okay. So another aspect that we need to point out is that this is the Fisher information for the n random variable here. But what we evaluate here, I also put a 1 here. It's referring to one single particular random variable. So to evaluate or to express the Fisher information for all n random variables for this particular parameter interest, we just need to multiply by n. Yeah. For that, resulting in n over 2 sigma raised to the power 4. Another way is that if you want, you can also express your likelihood function in an n-dimensional multivariate normal, and then so express this in terms of a multivariate normal probability density function, and then if you take a derivative with respect to the sigma square, you would directly end up with this form. But here, because we started with a scalar form, so in the end, just don't forget you need to multiply by n to get the multivariate case. Because the definition for the S squared, it's a summation from 1 to n, so you need to consider all n's random variables here. Okay. But if you started with the multivariate normal and then using the same procedure evaluating the negative expectation, you will also get the n over 2 square root sigma raised to the power 4. And then one final to finish on the numerator, it's just 1 over that, and then 1 over n over 2 sigma raised to the power 4, so that the numerator is just 2 sigma raised to the power 4 over n. So this is the numerator. Okay, so that is the numerator. So already the 1 over the Fisher information matrix, the particular entries in your 2x2 Fisher information matrix. Okay, so now we also need to evaluate the denominator, which is the variance of S squared, and then we're taking the ratio to compare whether it's greater than or less than 1. Okay, so any thoughts or comments on how to evaluate the variance of S squared here? Sorry, can you say it again?
Start from chi-square, since n minus 1 square over sigma square follows chi-square.
Yeah, that would be, yeah, I think that's, from there, you basically just derive everything from scratch, right? And then you're starting from chi-square. I'm not sure if the professor comments or showed that what is the distribution for S squared in the lecture. Well, chi-square is also a special case for gamma, so yeah. But that is just, you started everything from scratch. But here we can just, I'm not sure if this is given or, if it is given, then we can directly use it. But I'm not sure if anyone, so the distribution for S squared is also, is a gamma distribution. Is this given or derived in the lecture, or?
Yeah, it's in the
Okay, so then I can assume that you have seen this, right? Okay. So then I will just like specify or write it down as a given. So S squared is just a gamma distribution with the corresponding parameters, which is n minus 1 over 2 for the alpha, and then 2 sigma squared over n minus 1. So it is something that is derived or given from the lecture. So I can also assume this looks familiar to you guys, right? And then, okay, because the rest, for evaluating the variance of S squared, we are going to use information from here. Okay, so yeah, so then I would just assume this is given. So S squared is is following a gamma distribution with this particular alpha and beta. Okay, so we're interested in the variance of a random variable that follow a gamma. So what is the variance for a gamma random variable?
Alpha beta squared.
Yep. So just alpha beta squared, and then we can just plug in. But if this is not given, then you would just need to derive like from the chi-square or moment function to show that it's going to be a gamma. Yeah. But here I'm just assuming this is given, and we know this is alpha beta, and then we can just plug in here. Okay. So we have n minus 1 over 2 and beta squared. Okay. So maybe I can write 2 sigma squared over n minus 1 and taking the square. And this should end up with also a 2 multiplied by sigma 4 and then one more copy of n minus 1. Okay. Yeah. So that would complete our denominator. And next we just need to take the ratio. So 2 sigma raised to the power 4 over n, and then over the 2 sigma raised to the power 4 over n minus 1. So this should be n minus 1 over n, and then we can see that this is less than 1. So I think this is what the question wants to show. So show that the efficiency of S squared is less than 1. Okay. Yeah. Any question or comments on this part? Okay. Next, here I want to point out another thing is that for exercise 2, this question is also given in stats 100B, which is also in another video that I already posted. And then it seems like I spent the entire 15 minutes for 100B on this question. So this question is a very long and computationally intensive question. So, but I already made a video. So maybe if you're interested, or if you want to, if something is unclear to you, then you can revisit that video. I think that I give a very 15 minutes working on this entire question. So yeah, exercise 2 for this homework A. This is a very computational intensive question. So for lots of details, I think you can revisit that, because if I started here, I don't have time to finish question 2.
Did you post that?
I already posted. It's for the 100B, and then from their discussion from last week.
It's on YouTube channel.
Oh, okay.
Yeah. Oh yeah, but I just want to say that.
You have like a lot of subscribers.
See,
On
Uh,
that channel, because of all this.
Oh, but it's not. I cannot. It's for free, so I did not turn on any. Yeah, I mean, it's just. Yeah. Oh yeah. That is just for promoting free education, so that people can see it online. Yeah. Yeah, but what I'm trying to say is that this it might take 15 minutes for me to start it from scratch for entire question. So exercise 2 is very. So if you are interested in the details, maybe you can visit that video. But it's very computationally intensive, just for this question. Yeah. Okay, so we also have the solution for that, and maybe we can talk about exercise 3. Okay, so let's take a look. So x1 to xn IID, general, normal, mean, mu, and sigma. Answer the following question. So theta hat is x bar s squared, and then it's an unbiased estimator for that. Find the variance of that. Okay. So so we first need to verify that. So again, whenever we want to verify it's an unbiased estimator, we just take the expectation of the estimator and then see if it's equal to this mu multiplied by sigma squared. Okay. So yeah, I think that should already have set up the question for exercise 3. So what we want to do is that the expectation of theta hat and then check whether it's going to equal to what was it? Mu sigma squared. Okay, so that would be the question that we want to solve. And theta hat is just x bar multiplied by s. Okay, so one more thing. Here I'm also assuming this is also given or derived in the lecture, is that x bar is independent of s squared. So I think this is also shown or proved or derived in the lecture, because this is also a key information that we want to use. Okay. So that'll be the question, that'll be the estimator, and then this is additional information that we need to use. So again, expectation of theta hat, and then we can just plug in the definition for the estimator. X bar multiplied by s squared. So here, because they're independent, then we can write it as a product. Expectation of x bar and then expectation of s squared. Okay, let's see what else we can comment on here. X bar. Okay, so now we need to revisit the definition for x. Each of the xi follow a normal, mean, mu, and the sigma, standard deviation here. Okay, so what is the expectation for x bar? Mu. So maybe we can write x bar also a normal with mean, mu, and the sigma squared over n. So the expectation of x bar is mu. Okay, so that's that. And then multiply by expectation of s squared. So I think we, so we comment that s squared following a gamma distribution, n minus 1 over 2, and then sigma square, 2 sigma square over n minus 1. Okay, so once we know the distribution, what is the expectation for E of s squared?
Sigma squared.
Okay, so then this is okay, assuming that you also know that. Okay, so yeah, if this is already known or given to you, then you can just directly plug in sigma squared. Yeah. Okay. Otherwise, you need to prove things and then to. I was thinking about alpha beta, yeah. But if this is already given, then you can just plug in. Yeah. And yeah, I think it already shows it. Okay. Expectation of theta hat equal to mu sigma squared. Yeah. So I think that should complete the first part. Verify that theta hat equal to that is an unbiased estimator. Okay. Next step, find the variance. So we need the variance of theta hat. Okay, and then plug in variance of x bar multiplied by that. Yeah. So any thoughts on how we can address this one? So both of them are random variables, but we know their distributions, and then we're interested in the variance of the product. Any thoughts? Okay, so one way we can do, so lots of this question, there are multiple ways you can address this. So one way we can do this is that we can use the second moments minus the square of the first moment. And then that's that. So the expectation of the square of the product minus the square of the expectation of the product. Okay. So let's see what else we can do here. I think this is already given, or we already have that from part 1. So we just need to worry about the first term. So maybe we elaborate a little bit. So x bar raised to the power of 2, and then s s squared, and then raised to the power of 2. Closing that, and then the second term. So I think the second term you can directly get the answer from first part. So mu multiplied by sigma squared, and then raised to the power of 2. Okay. Any thoughts on comments on the first term? So we reduce the variance in terms of expression involving expectation. So what else we can do here? Yep. So we can write it as a product. So s squared, and then another square for that, minus mu squared sigma, I'll just write power 4. And what is the expectation for x bar squared? Any thoughts on this term here? So we know the distribution for x bar is a normal. Then how can we approach to the square of this random variable? So we can do variance of x bar plus expectation of x bar squared, right? Yeah, similar procedure as this one here. So that's sum, and the sum multiplied by the expectation of s squared square minus mu squared sigma raised to the power of 4. Okay, so here we have the variance of x bar and the expectation of x bar. And for this one, we can just plug in. So what is the variance of x bar here? Sigma squared over n. Right. What is the expectation of x bar? Mu and then square. Yeah, that's that. And now the question, or the next, we just need to worry about this one. So we have a gamma random variable, and then raised to the power of 2. So how can we address this term here? Any thoughts? So e of x raised to the power of k, where x following gamma, alpha, beta. How can we address this one? Any thoughts? There's a formula, the formula for the kth moment, right? Yeah. So here we're just evaluating a kth moment, and then we can just use the formula alpha plus k, beta k over gamma of alpha. I'm not sure if this is one of your previous homework question or should also be provided in the lecture. So basically just a formula, and that is the formula that we want to apply here to address this term here. So yeah, we just need to plug in the corresponding term. So for the, let me just move up. So for the numerator, which is a gamma function of alpha, alpha in our case is n minus 1 over 2 plus k. K should be 2. So this 2 here is the k. So plus 2 multiplied by beta. Beta in our case is 2 sigma square over n minus 1 raised to the power of 2 k. So k is 2 in this here, and then over a gamma function of alpha, so which is a gamma of alpha which is n minus 1 over 2 in our case. Okay, and then everything together minus mu squared sigma power 4. Okay, so now we express everything explicitly in terms of all the parameters. So they're all either involving sigma, mu, and n, and constants. So the rest, it just simplifies. Yeah, any question up to this point? Yeah, so just to summarize, we are interested in the variance of the estimator, and the variance of the estimator is a product of two random variables. And then we are going to decompose this variance in terms of the expectation of a second moment minus the square of the first moment. And then, yeah, so, and then this is coming from the previous parts, from the first half of the question. And then this to this, we have the independency. We can write it as a product of the two expectation. And then we apply the square root, the second moment minus the square of the first moment again, this formula resulting in that. And because we know the distribution for x bar, we plug in the formula. And here, this is a gamma random variable raised to the power of kth moment. And then we just use the formula to plug in to evaluate that. And then we have this. Okay. So here, let me just write down the final solution. And then you can just simplify that to check whether you have the same answer. So this should be sigma squared over n plus mu squared. And okay, yeah, maybe let me just elaborate a little bit. So there's another formula that you can use for this term here, which is n minus 1 over 2 minus 1. And this is a gamma function of n minus 1 over 2 minus 1 over a gamma function of n minus 1 over 2 multiplied by 2 sigma squared over n minus 1 altogether squared minus mu squared sigma power 4. So the formula that we use here is that a gamma function for alpha plus 1 is equal to alpha multiplied by gamma function of alpha. I think this is only valid for alpha in their natural numbers. Yeah, but gamma function itself is a definition of a integral of something, dx. But this formula is only applicable when alpha is a integer or a natural number. Yeah. For more details, maybe you can, yeah. But yeah. So that's the formula that we use here. So this is the gamma function, and then we minus a 1, so we can move it outside the constant here. And yeah, we also need to apply that again. So we have n minus 1 over 2 minus 1. And then we have a n minus 1 over 2. And then remaining a gamma function of n minus 1 over 2. So if you apply that again, it will cancel out with the gamma function in the denominator. So everything else stay the same. Multiplied by that, and then minus that. Yeah, so the final answer should be sigma squared over n plus mu squared. And then n plus 1 raised to the power of sigma 4 over n minus 1 minus mu squared sigma power 4. Yeah. So the things that I comment is that there are another rules for the gamma function that you can apply here to further simplify this this fraction. And that should be, and then I think there's no way you can further simplify from here. Okay. So again, just to, in case you forget, what we are showing here is the variance of the sigma, theta hat. Okay. Question or comments? let's see, find an unbiased estimator for theta equal to that. Okay. So for part B, here I'm just going to write down some high-level ideas, and then So if you define an estimator that is x bar over s, you will find the expectation of theta hat is mu over sigma raised to the power of 2 multiplied by n minus 1, n minus 3. So you can see that this is not equal to mu over sigma squared. So we need to define that the estimator theta hat is reciprocal of this one. So n minus 3 over n minus 1 x bar over s. And this is an unbiased estimator for mu over sigma squared. Yeah. Okay. So that should answer the first part. Find an unbiased estimator for that, and then find the variance of the estimator. So we want the estimator for this one. So the one that we designed. So n minus 3, n minus 1, and then x bar over s. Is it s or s squared? I think it should be s squared. Yeah. Yeah. So this is a constant, and then you just need to evaluate that. And then again, you need to use the independency so that you can reduce the variance. So first of all, you need to reduce the variance in terms of the expectation, and then you need to use the this kind of some additional informations, and then you can further write as something like x bar multiplied by the expectation of s squared raised to the power of -1. And then here again, the formula, this is a gamma random variable raised to the power of k for -1, and you can use the formula and then further simplify from there. So here I'm just giving a very high-level ideas on how you can address part B. Yeah. Okay, I think I'll just, I will just stop here. Yeah. But it should give you enough hints on part B.